Okay, so we begin with work and energy. When we speak about when work and energy, two things come to our mind is the uh, ability of doing something. And to do something, we need energy because without energy, we can't do any work. Okay, and it depends on what type of work we are talking about. Is it the work that we go to, or the activity that we do, or some amount of energy that is spent is referred to as work done. In this chapter, we'll focus on work as well as energy and the different forms of energy that help us to do different types of works, whether it is lifting something or pushing something, whether it is gaining a particular, gaining a particular form of energy. And energy can be of various types. Okay, they are not just one type. We don't refer to the strength that we've got as the only energy. Energy can be in the form of light, can be in the form of heat, can be even electrical energy, and so forth. There are various forms of energy. Energy we cannot create, neither can we destroy it, but we can change it from one form to another to make it useful to us. This chapter will touch upon those aspects of work and energy. Work. So, as I said, in day-to-day life, we do a number of things, and that it depends from one person to another what that person considers as work. Sometimes doing nothing also becomes work for some people. Okay, so in this case, the definition we are given here in general form is something useful physical or mental labor we regard as work. But in science, work is described or defined in a different way. So if it doesn't meet those criteria, according to science, work is not done. Okay, so both those criteria have to be met, and we'll see what are those criteria. So two conditions are needed to be satisfied for work to be done in science. Okay, first thing is a force should act on an object. So in other words, uh, it's like saying you need to put a certain amount of force onto something for that object to feel that force and do something. Okay, and the other thing is the object must be displaced. When we say object must be displaced, it means it should move from point A to point B. Let's say if we take a point at which an object is right now, okay, say if it is your mobile phone, which is now right now stationary, okay, and if you move it slightly, that we will record as point B. The fact that the point where this mobile of yours or the cell phone of yours was stationary, not moving, can be regarded as point A. When you move, it moves slightly. No matter how much is the distance it has moved, it will be regarded as moving from point A to point B, and that is called as a displacement. I will speak about displacement in the future slides. For now, two things we need to know as per science when it is regarded as work is being done is first thing the force should act on an object. Secondly, the object upon receiving that force or upon the force acting on that object should be displaced or should move from point A to point B. So if either of these condition does not satisfy, we say the work done is zero. So it is not it is not what do you say? It is not enough even if force acts as an object. The force of the that is acting on the object should be able to displace the object, and displacement can even be zero even after the object has moved a certain distance. Okay, and we'll touch upon that later on. So two things remember. One thing, for work to be considered done according to science, force should act on the object. Secondly, uh, the thing is that after the force acts on the object, the object should be displayed. That is when we say work is done. Okay. Work done by a constant force. So here we are talking about force that is constantly applied onto an object, and we are looking at measuring that work that is done, okay, by the force that is applied onto an object. Let's see how we measure it. Okay. First, we come to the definition of work done in terms of its units. So work done by 1 Newton force in displacing an object by 1 meter will be 1 Newton meter. Newton is the standard international unit for force. So how we weigh weight in terms of kilos or grams, and height in terms of meters, feet or centimeters. Similarly, we the unit of force, we measure force in terms of Newton. So if work done, it is said by 1 Newton force in displacing an object. So in moving that object, okay, by 1 meter will be 1 Newton meter. So that means that tells you that it is actually multiplied with each other. The force is multiplied with the displacement to give us work. That is why it is Newton meter and not Newton upon meter. The Newton meter shows you that force is multiplied into the displacement. And if you notice the displacement of that object, the unit is given by meter, same as that of distance. But we'll soon learn as to what is the difference between displacement and distance. They are not the same, though they may look the same. They are not the same. So unit of work is Newton meter, or we also refer to it as joule. Okay, say 1 joule of work is done when 1 Newton of force displaces an object by 1 meter. Okay, so either you can call it as 1 Newton meter or 1 joule of work is done when 1 Newton of force displaces an object by 1 meter. Now, work is a scalar quantity. We've learned previously about scalar quantities and vector quantities. Okay, so scalar quantities do not have direction. Okay, whereas vector quantities, on the other hand, have got direction. Scalar quantities has only magnitude. Okay, and work is a scalar quantity. So whether in whichever direction the work is done, uh, it does not affect or influence the work that is done, because it is a scalar quantity dependent only on the magnitude of work done. Okay, that is the amount of work done, not in the on the direction. On the other hand, when we speak about displacement, okay, that displacement, the direction matters. In which direction? If in case of a displacement we mean moving, okay, moving a particular object from one point to another. If displacement is in the direction of force, okay, so let's say I'm applying this force, and so the object will move in that particular direction. Like say pushing of the car, okay, when a car breaks down, you push the car, right? So when you push the car, when you apply the force from behind the car, what happens? The car does not move onto you, but it moves in the direction in which you are pushing, right? So you are applying the force in the forward direction, and the displacement is in the same direction as that of the force being applied by you to move that car. You want a car to move forward, so that's why you are applying the force from behind, okay, in the forward direction, and the car, as a result of which, moves forward. So if that amounts to certain amount of displacement. So if displacement is in the direction of force, it says, then work is taken as positive. Then work done is positive. Then if displacement is in the opposite direction of force, then work is taken as negative. Okay, that's where we come to the physics part of it. When displacement is in the direction of the force applied, then we say work done is positive. But if the displacement is in the direction opposite to that of the force being applied, then we say that work done is negative. And if you have a look over here, you have two formulas over here. They mean the same thing actually, but um, when we have displacement and distance as the two words over here, it does have an impact. So let's say first, in the first case, we say work done is equal to force into displacement. Okay, force into displacement. So in this case, the display, what type of displacement matters, whether it is positive or negative. And positive means the displacement has happened in the forward direction. Negative means it has happened in the reverse direction. Okay, opposite to that of the force. And force can also be regarded as the product of force into distance. So force into distance and force into displacement are almost the same, but remember distance is a scalar quantity, whereas displacement is a vector quantity which has magnitude as well as direction, whereas distance has got only magnitude, there is no direction in that. It's like saying like, okay, I'm asking you what is the distance from Mopsa to Panjim, and all I say is 12 kilometers. Here it does not give us any information as to which direction is 12 kilometers. Is it east, west, north, south? Nothing. Okay. But when we come to displacement, displacement will actually give you the idea as to which direction that would have happened. So distance does not give you a clue about the direction. It is a scalar quantity, whereas displacement will tell you the direction of displacement, in which direction it has happened. It is where in which direction force has been applied. So you look over here in front of you to explain. I had just mentioned to you in before that even though we have traveled a great distance, sometimes the displacement is zero. Now, I'll explain this part over here so that you understand the difference between a distance and displacement. Though this is given over here, a distance is going a zigzag way to reach B, and displacement is a straight point from A to B. What displacement can be zero, okay? Because displacement takes into account the starting point and the final point, okay, and the difference between the two, that is what it takes. But in case of distance, it will, let's say for example, okay, even if I remove this part, let's say I remove this curved part and we only consider A to B straight line, okay. Now distance and displacement from A to B will be the same. Let's say this is like 10 kilometers from A to, from point A to point B is 10 kilometers. So the distance is 10 kilometers. How much would be the displacement? It would be 10 from A to B. But what happens if, let's say, a vehicle moving along this highway A to B, which is 10 kilometers, if the vehicle travels from A to B and then from back from B to A, in such case, what would happen? What would be the distance? Distance will be 10 kilometers to go from A to B and 10 kilometers to go from B to A. Means 10 plus 10, 20 kilometers in case of a distance. But in case of a displacement, the displacement would be zero. How? Because displacement actually is a sum of the final point and the initial, meaning that it's a difference between the final point and the initial point, the starting point. So if we take the final point was A, and the starting point was also A. That means, as per science, displacement is zero. But in case of the distance that is being traveled, yes, the displacement is, because we, in displacement the direction matters. So you see over here distance tells you it is a scalar quantity and it refers to how much ground an object has covered. That is why we say 10 plus 10, it would become 20 kilometers. But in case of displacement, which is a vector quantity, you see, it refers to how far out of place an object is. So if the object started from A, if the vehicle started from A, and after going back to B, it has returned back to A. If we go by this definition, how far out an object, how far out of place an object is, out of place. It is not out of place. It is back to the same place, right? Because it moved from A to B, and from B to A, it returned back. So, which means it was not out of place. And if it is not out of place, that means displacement is zero. But that is not true in case of the distance, right? Distance, because it went here, it came to B, and from B it returned back to A. So 10 kilometers it took, drove from A to B, and then back it was from B to A. So it is, in case of displacement, what is looked at is the object's overall change in position, okay, and not as to much how much ground is covered, or how much distance is covered. Okay? So there's a difference between distance and displacement. So remember, this can actually come, for example, though that the fact that though an object has moved a certain distance, the displacement is zero. That is because displacement deals with the how far the object is out of position uh, from the initial point or the starting point. Energy. Okay, coming to energy, an object having a capability to do work is said to possess energy. Okay. Now, uh, the if we do not possess energy, we won't be able to do work. But energy does not is not limited just to human beings or animals or plants. Everything, every living and non-living entity possesses some amount of energy. The form of energy may be different, okay, from one individual to another, I mean, from one living entity or non-living entity to another, but everything possesses energy. So energy is present in various forms. As I said, energy can neither be created nor destroyed, but it can be transformed into one form of the or the other. So the object which does work loses energy. And in accordance with the law of conservation, the object on which work is done gains energy. So what it's trying to say over here is energy is never lost. We never lose energy. Okay, we never lose energy, as in an individual may lose energy to someone else. Okay, like for example, if I try to push a table, I am losing energy, but that energy which I lost is actually not lost, because that energy is gone into the table, scientifically speaking. Okay, that energy is absorbed by the table, because of which work is done in moving the table from point A to point B. We've been able to displace the table, or move the table from the place where it was stationary to another place. So in this case, what happens? The energy from you gets transferred to the object or the individual on which the energy was used. Okay? The energy possessed by an object is measured in terms of its capacity of doing work. So unit of energy is therefore the same as that of work, and that is joule. So we learned that the unit of work was Newton meter or joule, right? So here we can say that though energy and work are interrelatable, interchangeable, we can say that the unit of energy is is joule. Now there are different forms of energy. I've just categorized it into five main forms as per your level, and we can easily remember them if we uh, remember the mnemonics. This is mechanical, electrical, light, thermal, and sound. If you take out the letters from here, it will be M E L T S. So melts. Remember that these are the five main forms of energy for you. There may be other forms of energies also, but for you, the main thing to remember is these five, okay, which is M for mechanical, E for electrical, L for light, T for thermal, S for sound. Mechanical uh, has two other forms of energy which we'll be learning, that is potential energy and kinetic energy, depending on the ability to move or because of its position. You have electrical energy which supplies us with electricity, light energy mainly through sun, okay, thermal energy referring to the heat, and we use thermal energy in case of trains or in case of electricity to generate electricity. Thermal power plants are present in India and globally as well to power various industries and so forth. And you have, of course, sound energy. Sound, as I'm speaking now, I'm utilizing sound. Without we're utilizing a form of energy called sound. Okay, so there are also energies. That is why when we speak for a long time or we sing for a long time, tendency is that we get tired or we feel thirsty, is because an amount of energy is getting utilized in producing that sound. So, if in case of a vehicle that produces a lot of sound is said to lose a lot of energy. For example, a bullet and other bikes or even cars, which tend to make a lot of noise, these vehicles are actually losing energy in the form of sound. Coming to mechanical energy, before we stop over here, we'll move to potential energy and kinetic energy in the next class. But for mechanical energy is the energy that is possessed by an object due to its motion or due to its position. So you can take mechanical energy as a sum of both an object's motion as well as its because of its position. And we'll see over here what exactly is mechanical energy when we speak about energy possessed by an object due to its motion or due to its position. So as I discussed before and I mentioned before, that mechanical energy can either be kinetic energy or potential energy. See this kinetic energy, the name you may have come across, kinetic Honda, okay, which was quite popular during the 90s and even the early 2000s. And the name kinetic energy, kinetic Honda, came actually from this kinetic energy. And kinetic means movement, actually, motion. So energy possessed because of its motion. And you have potential energy, stored energy or energy because of its position, okay, where it is, where the object is placed. So here as you see, this is a small picture showing you about mechanical energy, how uh, kinetic energy and potential energy are related or classified under mechanical energy. Mechanical energy can be considered as a total potential energy and kinetic energy of an object. So you see a boy riding a bicycle over here, and he's at the bottom of the hill. So when you're at the bottom of the hill and you want to go on top, you pedal faster. Okay. As a result, you try to gain speed to reach up. Okay? If you try to do it slowly, you will never reach up. Okay? So you need to have some um, energy, and for that you need to put your energy into the pedals of a bicycle. That's when the pedals will move faster, and then the wheels of the bicycle will also move faster. So that's exactly what the rider is doing over here. He's cycling faster over here. That's why it says energy in. And you will notice as he moves up, uh, there's a lot of kinetic energy that he is actually utilizing. And then when he reaches right at the top, when he is at the top, he gains something called as potential energy. So kinetic energy gets transformed into potential energy mainly because of its position. Okay, mainly because of its position. So, but as he comes down, okay, as he comes down, the energy that was in the cycle is now expanded or like released, and you see the cycle moving faster. Once again, as it moves down, it gains kinetic energy. So you see, energy just keeps alternating from one form to another. Basically, energy is going nowhere. Okay, it's just moving from one entity to another or one object to and another. So this is about mechanical energy. Remember, mechanical energy was about is a sum total of potential energy and kinetic energy that is present within an object that is in question. So in our next class, we'll go into a little bit details about learning about potential energy and kinetic energy along with examples and also equations that help us uh, find out how much is the potential energy and how much is the kinetic energy. So this will be all in this particular class. If you like watching this video, please hit the like button, share it with your friends and classmates. Please subscribe to the channel and don't forget to click on the bell icon to receive updates. Thanks for watching. See you in the next video.